Okay, so far we've talked about measures of central tendency, which gives you a sort of a typical data value. We've talked about measures of dispersion, which gives you an idea of how spread out your data is. What we're going to talk about in this section is measures of position. And by position we mean basically position within the data set. And to give you some idea of why we might want to do this, let's consider the following situation. So we've got a college swimmer, a competitive swimmer's best time in the 100-meter backstroke is 45.3 seconds, and his best time in the 200-meter backstroke is 99.32 seconds. And we want to know in which race is he the better competitor. So maybe he has to pick just one of those two races. Which one is he more likely to place or win in? And of course, you can't go by the fact that it takes him longer to swim 200 meters because it should. Well, we do need a little more information than just what his best times are. Turns out we also know that if you look at all the competitive college swimmers, the mean time for them in the 100-meter backstroke is 48.62 seconds with a standard deviation of 0.98 seconds, whereas the mean of all the college swimmers' times in the 200-meter backstroke is 106.58 seconds with a standard deviation of 2.38 seconds. So it turns out that information is enough to give us some idea of which race he's more likely to win or come in ahead of more of the other swimmers. And here's how we're going to do it. We're going to use something called a z-score. And the z-score represents the distance that a data value is from the mean. So how far above or below average is this data value. So we're going to use that in a minute to determine how far above or below average are his best times in those two races. But it represents the distance the data value is from the mean in terms of the number of standard deviations. And what considering distance from the mean that way, in terms of not just like the numerical distance from the mean, but then in terms of the number of standard deviations, is it provides ways of comparing variables with different centers or spreads by converting them really to the same sort of variable with the same center, which is going to happen to be at 0, and the same spread, which is going to happen to be 1. Okay, and here's how we do that. If you're working with a population, your z-score within the data set for the population will be x minus the mean for the population. So x is whatever data value you're working with, minus the mean for the population divided by the standard deviation for the population. Whereas if you're working with a data set that's a sample, your z-score, it's the same idea, just the letters are a little different. It's the distance of your data value from the mean for the sample divided by the standard deviation for the sample. A few notes about z-score before we see an actual example. If a data value, in other words, this x here, okay, if x is larger than the mean, notice x minus mu will be positive. So if the data value is larger than the mean, its z-score is positive. If a data value is smaller than the mean, well, then x minus mu is going to be negative. So its z-score will be negative. Last, if the x value that you're working with, the data value, is equal to the mean, whether it's the mu for the population or x bar for the sample, if these two numbers are the same, you get a 0 on top. And if you have 0 on top of your fraction is equal to 0. Okay, so back to the swimmer example. For the 100-meter z-score, call that z1, 1 for 100 meter, is, okay, his data value, his best time, let's assume he's going to do his best time, is 45.3 minus, we're told that the mean for the population of all college swimmers is 48.62, and the standard deviation is 0.98. So I'm using this, I'm using the formula x minus mu over sigma. Okay, and crunching the numbers, we have minus 3.32. Notice his time is smaller than the average time, right? He's faster than average. So we get a negative number because this data value is smaller than the mean, and that's because he's faster than average. So we're going to get minus, about minus 3.3. Looks like that's a minus 3.39. Okay. What about for the, so this means that he is 3.39 standard deviations better than the average, right? His time in the race is 3.39 deviations below the average time, so he's that much faster. What about for the 200-meter race? Well, his z-score in that, let's see his best time, so we'll hope he's going to do his best time. His best time is 99.32. The mean time for all college swimmers in the 200-meter backstroke is 106.58, and the standard deviation was 2.38. So again, in this race, he's better than average, right? His best time is better than is smaller than the average best time, and if it takes you less time, you're going to win, right? So negative 7.26 divided by 2.38, so we get about minus 0.305. So in the 200-meter race, he's better than average, right? His time is smaller than average, but it's not, for the 200-meter race, it's not better by as many standard deviations as this one. So let me see if I can give you just sort of a visual of what's going on here. So say there's some hit frequency distribution. I don't know what it looks like. I'm just kind of making things up here. Let's say we've converted both the 100-meter and 200-meter frequency distributions into ones that have the same mean of 0. Remember, that's what this z-score kind of does, and the same standard deviation of 1. So it gives us a way of comparing where this guy's score, where this guy's time falls in terms of all possible times. So this is a frequency distribution, time in seconds. Okay, and we've, instead of, if we were to take all the data values, not that we were to have them, but if we were to take all the data values for the 100-meter race and make a frequency distribution and a histogram, and then we were separately to take all the data values for the 200-meter race and make a frequency distribution and a histogram, we'd have two very different frequency distributions and histograms. But by looking instead at the z-score, it's sort of like we've made them comparable, so we can think of it being sort of one that works for both of them in a sense. And what we've discovered is that, and again, I'm just going to kind of randomly pick points in here. We've discovered that his z-score, let's say it's negative 3.39, that's our z1, so that's smaller than our z2. Okay, it's the distance between the mean and z2 is only 3.05 standard deviations to the left, less than the mean, whereas for z1, it's 3.39 standard deviations to the left, so it's further to the left. Now, what that means is then, if you look at how many swimmers are faster than him, there aren't as many swimmers faster than him if you look at his z1 score than if you look at his z2 score. And again, the z1 score was for the 100-meter race, the z2 score was for the 200-meter race. So it looks like there are fewer guys that can beat him in the 100-meter race than there are in the 200-meter race. So the guys that can beat him are the guys that have a shorter time, smaller time, and there's not as many of them proportionately in the 100-meter race. So this is the one that's better. Okay, so let's see what you can do with z-scores. I've got a similar kind of question for you. If the mean height of a guy in his 20s is 69.6 inches tall with a standard deviation of 3.0 inches, and the mean height of a woman in her 20s is 64.1 inches with a standard deviation of 3.8 inches, who's relatively taller? A 75-inch tall man or a 70-inch tall woman? So you know, because men tend to be taller, a guy has to be taller before you call him tall, right? So that what we're getting at here is, well, you know, would you call this guy tall or would you call the woman tall? Who's relatively taller for their gender? And then a second question, just with slightly different numbers, who's relatively taller, the 67-inch tall man or a 62-inch tall woman? So this example's a little, this build your understanding problem is a little easier than the one I just did, because in the one I just did, you had to think of a negative number as being better than a positive number, because a negative number meant you had a shorter time to complete the race. Here, bigger is taller, you know, a higher number is taller. So at least go ahead, and if you're still confused about figuring out what these z-scores mean, that's okay. But at least figure out the z-score for the man and the woman in part A and the man and the woman in part B. Okay, just use the formula x minus mu over sigma. You can do that. And then take a minute to think about what those z-scores would tell you about the answer to the question. But if you feel confused about using the z-scores to answer the question, that's okay. I'll talk about that in the next video. Good luck.